This is number 1 of 12 videos which aim to give some appreciation of quantum entanglement. The first 2 videos look at what might be called classical entanglement and also aim to get to grips with ideas like spin, angular momentum and magnetic dipole moment, especially as they relate to the behavior of electrons in a magnetic field and also to their classical precession. Videos 3 to 9 begin by looking at the quantum mechanics needed to further the discussion, and end in video 9 with what is hopefully a clear appreciation of the magic of quantum entanglement. All this will be done by considering the quantum mechanics of pairs of electrons. The last 3 videos, 10 to 12, will discuss the ideas behind some of the experimental tests which have been performed to look at alternative explanations for the phenomena seen. In other words, alternative explanations to quantum mechanics. Those tests will require a shift from thinking about electrons to thinking about photons, hence the need for 3 videos on the topic. To follow this whole set of 12 videos, you'll need some very basic background in a number of physics ideas. Basic magnetism and the magnetic effects of an electric current. Basic mechanics and the ideas shown here, along with simple ideas about vectors, especially components, vector addition and that kind of thing. Most of the work will focus on electrons and their entanglement, although much later on, when looking at Bell experiments, the discussion will centre on photons and linear polarization. Complex numbers will also feature here and there, and also very rarely complex exponentials. The discussion will include ideas about quantization and probability, and although these will be introduced and should be fairly easy, if you've never met things like electron transitions in atoms before, then some of these ideas may seem quite bizarre. So here goes. I'm going to start off forgetting about quantum mechanics and looking at a simple, almost childish example of classical entanglement using magnets. As you work through later videos, you should begin to see that although quantum entanglement has some similarities to this very simple classical case, there is a magic to it that is quite fascinating. But that's a long way off. Let's start with this simple and very obvious example of classical entanglement. Imagine 2 small bar magnets some distance apart. The 2 here have their north poles marked in red and their south poles in blue. They could be at any angle to one another. If they're pushed gently towards one another, there'll come a point, especially on a very smooth surface, when the force between them becomes appreciable and they will twist and turn, the like poles repelling and the unlike poles attracting, and eventually they'll rush together so that the north of one sticks to the south of the other. They could end up vertical like this, or at some angle to the left or to the right, or even into and out of the screen. They could, conceivably, rather than being side by side like this, be end to end and pointing in the same direction as each other. However, this would be a slightly higher energy state than being side by side, and if you've ever done this experiment with 2 bar magnets, you will have noticed that the rapid motion takes them to the lowest energy state, which is always side by side. Let's pick a direction and assume that they end up vertical like this, with the left magnet as we look at it having its south pole upwards, that's blue, and the right magnet having its north pole upwards, that's red. I'm going to say that these 2 bar magnets, when they're like this, are, in a very simple and classical sense, entangled. What I mean is, if we were then to pull them apart carefully without disturbing their orientation, they'll come to look like this. Now it's fairly obvious that if we look only at this magnet and we see that the south pole is pointing upwards, we automatically know without looking that the other magnet has its south pole pointing downwards and its north pole pointing upwards, assuming that they were not disturbed as they were separated. Now that's just trivial. In a way, they were fixed like that when they came together. They were what you might call entangled with one another. And the fact that we didn't disturb their orientation while moving them apart means that we know that they're bound to point in opposite directions when they're separated. It goes without saying, but I'm going to say it anyway, that if we did the same experiment starting with magnets at any old angle to one another and put them into fairly thin but opaque paper bags so that we didn't know which way they were pointing at any time, then we get the same kind of result. We could bring the bags with the magnet inside closer together. they would eventually stick, or rather the magnets would stick due to the forces easily penetrating the sides of the paper bag, and the magnets inside the bag would be, in a sense, entangled with one another. If we then carefully pull the bags apart without disturbing things, without the magnets moving in any way within the bag, we would have the magnets at some angle inside their bags, but we wouldn't know anything about the angle of either of them, assuming we couldn't feel them through the bags. We wouldn't know which one was up and which one was down, or whether they were left and right or whatever. We would know nothing about each individual magnet. However, if we then peeped into one of the bags and saw that the bar magnet had its north pole up, then without looking into the other bag, we would automatically know that the other magnet had its north pole down, assuming once again that the magnets hadn't been disturbed as the bags were separated. Looking at the orientation of one tells us all about the orientation of the other, all because they were entangled in this way. That's what you might call classical entanglement, and it's obvious. However, the entanglement of things at the quantum level, when things are extremely small, is a different matter, as we'll see much later on. Let me for now, however, consider a quantum system, a very small system, and let me treat it classically, in other words, in exactly the same way as we've been thinking about bar magnets. I will state as a simple fact, but we'll discuss it in some detail later, that electrons can at least be thought of as spinning negative charges which act like a small bar magnet. I must stress, though, that this is not a valid explanation of the origin of the electron's magnetic properties, but it is a useful picture to pursue, and you'll see this as we move forward. I've shown it here as a yellow ball which is rotating anti-clockwise looking from below, so a negative charge spinning like this means it's like an electric current flowing clockwise from below around in circles. Again, we'll discuss this later, but that means that the electron will act like a little bar magnet, and in this case will have its north pole upwards. I've shown it here by putting a red arrow through it, and the arrow points in the direction of its north pole, what would be the red end of the magnet. The direction of this magnet can be found by what is called the right-hand grip rule, again which we'll discuss later. For now, just accept that the spinning electron is like a little magnet. So in the same way that bar magnets can become entangled, we can think in terms of electrons as little magnets becoming entangled with one another if they come close. Let's consider a very hypothetical situation of two electrons separated by some distance. We show them here as spinning balls of negative charge which act like small magnets, and with their north poles pointing in different directions. That's the red arrow. We'll ignore the repulsion that there will be between the two electrons from the fact that they're two negative charges, and of course like charges repel. Forget that. We're also ignoring any kind of interaction there might be between their spin angular momenta. Just think of them as two magnets. I did say this was a hypothetical situation. If we brought them together, they would act like the bar magnets that we talked about a moment ago, and they would end up close to one another with their magnets pointing in opposite directions, again ignoring their electrostatic repulsion. Their spins would be pointing in opposite directions. They could be up and down, left and right, whatever, we don't know. We don't know because we can't see electrons. We can't know anything about them without disturbing them. Unlike the bar magnets, which can be looked at by shining light on them and viewing them, the electrons are so small that anything we use to try and detect them will disturb them, so we genuinely don't know the orientation of the electrons. But we do believe, I guess, that once they've been together in this way, they will be entangled in that their spins will be in opposite directions. In a sense, during the whole process of the electrons coming together, they would essentially be hidden from view. We know that we can't see electrons in the same way that we can see magnets. And to mimic that, let me put the electrons in paper bags for now and redo the hypothetical experiment. The bags come together, the electrons get entangled. Okay, it's silly, I know. This time we really do have no idea which way they're spinning and which way the north and south poles point. Once again, if we could carefully pull the bags apart without disturbing things, we would have the electrons at some angle hidden from direct view. We really wouldn't know anything about the angle of each one. We wouldn't know whether they were into or out of the screen, up or down, left or right, or anything. However, if we then somehow detected one of the electrons and measured its magnetic direction, effectively peeping into one of the hypothetical bags, and if it had its north pole to the right, say, then without making a measurement on the other electron, we would automatically know that it had its north pole to the left. Making a measurement of the orientation of one tells us all about the orientation of the other because they were entangled in this way. Now I realise that all that seems extremely obvious, whether we're talking about bar magnets or whether we're imagining experiments with hypothetical electrons. It's obvious because we naturally believe that once two magnets or two electrons are entangled in this magnetic way and then separated, they each carry a fixed direction with them, provided no one interacts with them to change it. The bar magnet, as it's moved apart, is pointing in a particular direction. Similarly, thinking classically, the electron, as it's moved apart, is pointing in a particular direction. All of that very simple discussion assumes classical, everyday physics and what we might call common sense. However, quantum mechanics is not common sense, and quantum entanglement is very different from that classical kind of situation. The rules of quantum mechanics are bizarre. For one thing, you usually wouldn't know with certainty which way an electron's magnet is pointing until you measure it. Once you measure it and you know it, then you can assume its entangled partner is in the opposite direction. Now you may understandably say to that statement, so what? It's just like opening the bag on the bar magnet. Surely, when the electrons are in the process of coming apart, they still have their directions. It's just that no one knows them until a measurement of one of them is made, which is like looking in the bag. You might go on to say the electrons carry that information with them, just like the bar magnets did when they were travelling apart, and then when you measure the electrons, they give that information to you. It's obvious. And the trouble is, it's not obvious. That is not the case. There's more to it. There's a subtlety. There's almost magic in the air, and it all stems from the weirdness of quantum mechanics. If you think classically, as we've just done, this kind of entanglement of electrons seems easy to explain. It's obvious. The magnets of the electrons are fixed when they get entangled, and they stay like that until they're measured. However, it's only when you delve into quantum mechanics that you realise that this can't be the case. So, part of our job here will be to do enough quantum mechanics as simply as possible in order to realise the extent of the problem with that classical explanation. The explanation that's fine for bar magnets, but actually isn't fine for quantum systems like the electron. We need to appreciate why it's not fine, why we can't simply use that classical explanation when dealing with electrons. Once we've accepted that, we can then get on to think about how quantum mechanics might give us some explanation, or rather appreciation, of the reality of the situation. Now, before we tackle any of that, however, I think it's important that we have some understanding of terms like spin, angular momentum, magnetic moment, and a few other things. These terms are going to crop up again and again, and we may even inadvertently slip from talking about one of them to talking about another. So I think it's important to have a clear concept of each of them. And with this in mind, there now follows a rather long digression to get to grips with the basics of all that. Let's start that process with some classical magnetism. If you're sure that you know enough about spin, what spin angular momentum is and what spin magnetic dipole moment is, then you can probably skip the next few sections of this classical discussion, but personally I wouldn't advise it. Anyway, consider a magnetic field B produced from two large poles of a magnet, south at the top and north at the bottom, and let's assume that the field between the poles is uniform. In other words, it's the same everywhere. The field lines will go from north to south, in this case upwards, and because the field is uniform, the field lines will be parallel and equally spaced apart. I'll get rid of them for now to reduce the clutter. If a bar magnet is placed in this magnetic field, let's say like this, with its north pole shown in red and its south pole in blue, then its north pole will experience a force in the direction of the field, and its south pole will be pulled in the opposite direction. These two forces will be identical in size, providing the magnetic field is the same everywhere. In other words, providing the field is uniform, and we obviously assume the two poles of the little bar magnet are equally strong. In simple terms, these two forces can be thought of as being because the external field is due to a north pole at the source of the field lines and a south pole at their destination. The small bar magnet then has its north pole attracted to the south of the external field and repelled from the north, and it has its south pole attracted to the north of the field and repelled from the south. If the magnet is positioned so that it is parallel to the field B in the way that's shown here, and the field truly is uniform, then these two forces will be equal and opposite and in line. And so they will have no noticeable effect on the magnet. They will balance one another out. However, if the bar magnet were to be positioned at some angle to the uniform field like this, then the two equal forces, which are now not in line, will constitute a couple, or a turning force. They will try to turn the magnet around, in this case clockwise as we look at it. The strength of this turning force, or couple, is called the torque, and is given the Greek letter tau. The size of the torque is defined to be the value of one of the forces, F, multiplied by the perpendicular distance d between the two of them. Tau equals Fd, where d is the distance shown here, the perpendicular distance between the two forces. The distance d, of course, will depend on the angle of the magnet to the field. It will be greater at some angles and smaller at others. In fact, it's easy to show from trigonometry that d, the perpendicular distance between the two lines of action of the force, will depend on the sine of the angle theta between the bar magnet and the field, as well, of course, as on the strength of the magnet itself. It's also easy to demonstrate experimentally that the forces, and hence the torque, will depend on the strength of the magnetic field B in a proportional way. In other words, if you double the field, you will double the turning force, and so on. So fairly obviously, I think, the size of the torque, or turning force, tau, on a magnet will be proportional to B sine theta. Here I've lumped anything to do with the bar magnet, its length and strength of its poles, into the constant of proportionality within the proportional symbol. What we're saying with this relationship is that for a given magnet, the turning force on it, the torque, only depends on B sine theta. In fact, it's proportional to B sine theta. If you need convincing of this relationship, you could easily demonstrate it by a few experiments. Keep the angle constant, and vary the field, and measure the tau, the torque. And a plot of tau against B would give a straight line through the origin. Similarly, keep the field constant, and vary the angle, and measure tau. And plotting tau against sine theta would give a straight line through the origin. This is a fairly straightforward proportional relationship. Tau proportional to B sine theta. The constant in this proportionality depends only on the bar magnet, the strength of its poles, and of course how long it is. In other words, if the magnet is made stronger and longer, then the torque will be bigger, and vice versa. We will assign the letter mu to the constant in this equation. We'll call it the magnetic dipole moment of the magnet. A long or strong bar magnet will have a large magnetic dipole moment, whereas a short or weak magnet will only have a small one. Using this constant mu, we could then write the formula for the torque on the magnet as tau equals mu b sine theta. This magnetic moment, mu, we'll drop the word dipole from now on. This magnetic moment is considered to be a vector in line with the magnet, pointing from south to north inside it. You can think of the magnetic moment mu as a measure of the magnet's ability to turn itself to come in line with the magnetic field that it may be put into. Some magnets will have a large magnetic moment, and weaker or smaller magnets will have a small one. If the language is confusing, especially that word moment, bear in mind that even if the magnet is not in a magnetic field and therefore doesn't have any turning force on it, it still has a magnetic moment, mu. The magnetic moment is a property of the magnet. It's only when you put the magnet in a magnetic field that it experiences a turning force, which we could casually call a moment or a couple or a torque. Looking at this formula, tau equals mu b sine theta for this, it should be clear that when the bar magnet is at right angles to the field, say when theta is 90 degrees, then sine theta is 1. At that point the torque will be at its maximum value. This is because the two forces will be at their furthest apart. Force times perpendicular distance will therefore be the greatest. Also, of course, when the bar magnet is parallel to the field, either upside down, as I'll call it, at 180 degrees as shown here with its south pole at the top, or when it's the right way up at 0 degrees with its north pole at the top, then the torque will be 0. This is because when theta is 0 or 180 degrees, sine theta is 0, and the two forces are equal and opposite and in line. The perpendicular distance is 0, and so the force times perpendicular distance must be 0. You'll realise, I'm sure, that in the 0 degrees situation, when the north of the bar magnet is at the top, not only is the torque 0, but the magnet is stable. We have a kind of stable equilibrium. On the other hand, in the 180 degrees situation, when the magnet has its south pole at the top, even though the torque is 0, the magnet is in an unstable situation. It is in unstable equilibrium, and it's likely to flip through 180 degrees to get itself pointing what you might call the right way. Anyway, at some point in between those positions we have the magnet at some general angle theta to the magnetic field, and we have a turning force or torque on the magnet given by the formula tau equals mu b sine theta. In the situation shown here, it will be a clockwise torque. Now you need to realise that this torque, tau, although I've been showing it as a curved arrow, is really a vector. If it doesn't sound too stupid, this turning force should be represented by a straight line vector. In the situation shown here, the straight line vector which represents the torque should be shown pointing into the screen. How do we know that? Well, it's a convention. It's a convention that the direction of the torque vector is found by what is called the right-hand grip rule. Imagine positioning your right hand on the side of the plane where the rotation looks clockwise. In this case that means in front of the picture we see here on the screen, this side of the magnet. Then adjust your right hand so that your fingers go around in the direction of the rotation. Once you do that, your thumb will point in the direction of what you might call the torque vector. Here, your thumb would point through the screen from front to back. That's the direction of the torque vector in this case. That's the direction of this clockwise turning force, tau. Try to get used to that if you're not already. Any turning force or torque is always represented by a straight line vector. If you want to know which way it's trying to turn, you put the thumb of your right hand in the direction of the torque vector, and your clenched fingers will tell you the direction of the rotation. So, we now have a formula for torque which actually has three vectors in it. Tau equals mu b sine theta. B is upwards, mu is in the direction of the bar magnet, south to north, and tau is into the screen. Those who've studied physics to a high level will realise that this multiplication, whereby when you multiply two vectors you get another one which is perpendicular to the plane of the first two, is known as the vector cross product of mu and b, and it can be written like this. It's a special kind of multiplication of two vectors which has a maximum when they are perpendicular to each other, and we read this as tau equals mu cross b. When you understand how to interpret this kind of formula, you know that it contains within it the sine theta. When you follow the rules of vector algebra, you also realise that this cross product formula contains not only the size of the torque, mu b sine theta, but also gives the direction of the torque. In this case, the cross-product formula tells you that the torque is into the screen at right angles to both mu and b. For that reason, I ought really to put some indication that these three things are vectors. And one way to do that is to put a line over them like this. But I won't do this from now on. In order to find the direction of the torque from this formula, the convention is to use the right-hand grip rule again, but you use it on mu and b. If we look at the situation with the magnetic moment vector in the magnetic field rather than the magnet, then in order to find the direction of tau, you imagine rotating the fingers of the right hand from mu to b in the plane of those two vectors, the plane of the screen in this case, and your thumb will then point in the direction of the torque, tau. Again, for this example, it means imagining your right hand in front of the screen, you make your fingers point around from mu to b, and again your thumb will point into the screen to give the direction of the torque. In that way, you can, in a sense, get the direction of the torque from the cross-product formula. Right, having got some idea of what we mean by magnetic moment, or strictly speaking magnetic dipole moment, we ought now to think about the unit that magnetic moment is measured in. The easiest way to do that is to use the formula torque equals mu cross b. Ignoring the fact that the cross bit here sort of includes the sine theta, you can rearrange this formula as mu equals tau over b and then think in terms of units. In doing that, it's fairly obvious that mu must have the unit for torque divided by the unit for magnetic field. As for the unit of torque, it's Newton meter, force times perpendicular distance, and the unit for magnetic field is Tesla. So the unit for magnetic moment must be Newton meter per Tesla. You could also call them joules per Tesla because the Newton meter is a joule. This is true even though the joule as a unit of work is to do with force times distance moved in the direction of the force. And of course, for the idea of torque, we have force times the perpendicular distance in our calculation. It matters not. The Newton meter unit for torque can still be written as the joule unit here. But there's more. You will probably know that there are lots of relationships between different quantities in physics, and so units can often be written in lots of different ways. And it turns out that the units of magnetic moment mu can also be written as ampere meter squared. So it can also have something to do with current times area, and we'll be thinking about that later. However, before we do, let's stick with this magnet situation and think about some energy considerations. We said before that a magnet in a uniform field like this, with its magnetic moment in the direction of the field, is in equilibrium. It's not going anywhere. The up force equals the down force, and there's no turning force because they're in line. There's no torque. This is the lowest energy state of the magnet in this system, and the state to which it will always try to end up. In fact, if you wanted to turn the magnet, you'd have to do work against the magnetic forces. You'd have to pull it in the opposite direction to the arrows, working against the magnetic forces, pulling the red end down and the blue end up, and then you would need to hold it in the new position because it would want to flip back to the upright position. The state of the magnet held in this new position has more potential energy than when it was parallel to the field. Turning the magnet even further to 90 degrees would require even more work, and to 180 degrees even more still. Suppose we take the initial potential energy in the equilibrium position to be zero. In other words, when the bar magnet is upright and stable and at 0 degrees to the magnetic field. This is the minimum energy it will have, and so I will define it as the zero of energy. In fact, let me show it as the magnetic moment vector rather than as a magnet, as it shows the direction more clearly, having its arrow head at one end. It's easy then to calculate that the energy needed to turn this magnet, or this magnetic moment, through 90 degrees is just mu times b, and also that the energy to get it to 180 degrees is twice mu times b. Now this is a very easy calculation. You simply consider the work done in rotating the magnet from 0 to 90 or 0 to 180. And here's one way to think about it very quickly. Consider the magnet at 0 degrees. To move it to 90, you would need to push down on the North Pole with the force F and push up on the South Pole with the same sized force until you get to the horizontal. At the start of doing that, of course, you'd need to be infinitesimally to one side of the vertical so that the two forces weren't just pushing directly against one another, but you could ignore that infinitesimal starting turn. To get to 90 degrees, each force will have to move a distance of half the length of the magnet in the direction of the force. Never mind that it's turning, and you have to change the force contact point sideways. That's immaterial. The forces are up and down, and the distance moved by each of them is half the length of the magnet, up or down. This is equivalent to one of the forces pushing the whole distance d, so that the work done to get to 90 degrees can be written as F times d. Yes, I know this looks like the torque formula, but in that case the force was perpendicular to the distance we were talking about, whereas here they're in the same direction. Work is being done here to turn the magnet. This is not the calculation for the size of the turning force tau, it's the formula for the work done when the magnet actually turns through 90 degrees. Having said that, I can still compare the magnitude or size of this to the torque formula. They will be the same value even though they don't mean the same thing. The formula we had for the torque started off as force times perpendicular distance, but after defining the magnetic moment mu, we wrote it as tau equals mu b sine theta. This then, in magnitude terms, is the value of the work done to turn the magnet through the angle theta. If we want the work done to turn it to 90 degrees, then as sine 90 is 1, it means that the work done is simply mu b. That, of course, means that the potential energy at 90 degrees relative to 0 degrees is simply mu b. By a similar argument, you should see that potential energy at 180 degrees is 2 mu b. Anyway, these ideas about the potential energy of magnets or magnetic moments at different orientations in a magnetic field will actually be important later when we come to think about electrons in a magnetic field. Now, to move on with a few more classical magnet ideas. If you were restraining or holding back the magnet to stay in, say, this position, and you then let go, then the torque from the magnetic forces would turn the magnet back towards the equilibrium position. The magnet would rotate. Clearly it would then overshoot the central position, and as it did so it would get pulled back by an anti-clockwise torque, and this would go on backwards and forwards. It would end up oscillating backwards and forwards. This would go on until somehow the energy was dissipated in some way, assuming there was some kind of friction or air resistance somewhere. However, and here's where I'm going to introduce something that may seem totally irrelevant, suppose somehow the magnet was itself spinning around its axis. Suppose you could hold it in this position under tension, as it were. I can't really show this as a spinning solid object in 3D, but I hope you get the idea. I'll show it instead, perhaps, with an arrow around its waist. It's a totally imaginary experiment. You have to imagine that the magnet is spinning in mid-air and somehow we're stopping it from being pulled into the upright position by the torque from the two forces which are trying to align it with the magnetic field. If you were then to release the magnet from this restrained position, instead of oscillating back and forth, it would precess around the magnetic field lines, still moving from left to right as we look at it from the side, but also with the top and bottom moving in and out. The top and the bottom of the magnet would be travelling in circles. Viewed, say, from above, the motion of the North Pole at the top would be going in a circle. This difference between what a non-spinning magnet would do, namely simply oscillate back and forth, and what a spinning magnet would do, has to do with what is called rotational mechanics. Let me explain by giving an analogy. Most children are fascinated by a spinning top, and they wonder why it doesn't fall over. I say that because if you simply took the top and without spinning it tried to make it balance on its point, it would obviously fall over, perhaps this way or some other way, but it would fall. And that's obvious. And the reason for it, we know, is because when we try to stand it on its point, it is in unstable equilibrium. Granted, there are two equal forces and equal and opposite forces on it, downwards from gravity, acting on the centre of gravity at the top, and upwards from the table, acting on the point of contact, but the top won't balance like that. Any slight movement away from the vertical will produce either a clockwise, or in this case, an anti-clockwise couple as we view it, which will cause the top to fall over. However, if you start the top spinning and let it go, it doesn't fall over. Instead, it precesses around the vertical, around the direction of gravity. So just as you might naively have expected the spinning magnet to go straight to the up position and overshoot, so you might naively expect the spinning top to go straight to the ground or to the table, but it doesn't. Because they are spinning and they have angular momentum, the extra torque, which is trying to turn them either upwards in the case of the magnet or down onto the table in the case of the top, that extra torque makes them precess. So with the spinning magnet, rather than go straight to the position that you might naively have expected it to, it precesses around the magnetic field lines, the direction of the magnetic field. In the same way, of course, the spinning top precesses around the vertical, the direction of the gravitational field. In some ways, I think this is a strange phenomenon, and most thinking people, I think, are fascinated by why it should be. In order to have some understanding of it, you have to appreciate not only linear mechanics, where we generally look at forces and the motion of things travelling in straight lines, but also rotational mechanics, where instead we consider what might be called turning forces or torques, which act on things which are rotating. The way I like to look at it is that the set of equations we have for linear mechanics, which describes things moving in straight lines, are matched by a set of similar equations for things which are rotating, what you might call rotational mechanics. Here's what I mean. In linear mechanics, we measure how far something's travelled by measuring the distance or the displacement in a particular direction, and we often call it x. However, in rotational mechanics, we measure how far something has travelled by measuring the angle theta that it's turned through. In other words, distance travelled x in linear mechanics can be likened to angle turned through theta in rotational mechanics. Similarly, in linear mechanics, mass can be thought of as a measure of how difficult it is to get something to increase its velocity or speed, whereas in rotational mechanics, it's how that mass is distributed throughout the object that makes it easy or difficult to get it to spin faster. Mass m in linear mechanics can be likened to what we call moment of inertia in rotational mechanics. And moment of inertia depends on the mass of the object, but also depends on how that mass is spread out in the object. Velocity v, or dx by dt, the rate of change of distance or displacement with time in linear mechanics, is equivalent to angular velocity, omega, or d theta by dt in rotational mechanics, the rate of change of angle with time. Acceleration, dv by dt, or d2x by dt squared in linear mechanics, is equivalent to angular acceleration, d omega by dt, or d2 theta by dt squared in rotational mechanics. And then there's momentum. mv in linear mechanics is equivalent to angular momentum, I omega, in rotational mechanics. Notice that I put I instead of m and omega instead of v. Even things like kinetic energy, half mv squared in linear mechanics, is easily mapped over to a half I omega squared, which is the kinetic energy of a rotating object. Anyway, all of the equations of linear mechanics can be replicated in rotational mechanics, and the mathematics can be worked out in a similar kind of way. For example, Newton's second law in linear mechanics, F equals ma, or force equals mass times the rate of change of velocity with time, or mass times the double rate of change of distance with time, becomes in rotational mechanics torque, the rotational force, equals moment of inertia times the rate of change of angular velocity with time, or I times the double rate of change of angle with time. Almost every equation you can think of in linear mechanics has its equivalent in rotational mechanics, where you're thinking about things rotating rather than things moving in a straight line. Consequently, if you look at a spinning top, which would generally be at some angle to the vertical as shown here, and if you only consider linear mechanics, then quite understandably you'd say that the top must fall over. Even at a very simplistic level where people don't think about the upward force on the top by the table, they'd know that the force of gravity was acting downwards, and it would seem obvious that the top should fall over. Gravity would pull it down. Here I'm showing an arrow for the force of gravity on the top, and it passes through what I think is where its centre of gravity might be. That simple argument, of course, ignores the rotational mechanics that's going on. First, we have to say that there is also an upward force on the top from the table at the point of contact. And these two linear forces on the top from gravity and from the table constitute an anti-clockwise couple as we look at it. And so they can be replaced by a torque vector which by the right-hand grip rule must be out of the screen. Clearly I can't draw this straight line vector, so you have to imagine a torque vector tau pointing out of the screen, which is really the turning force that we know comes from those two forces on the top. The conventional way to show a vector out of the screen is with a dot in a circle, and if it were into the screen it would be a cross in a circle. So here's the dot in the circle indicating that the torque vector is acting on the spinning top and it is outwards. Now the top itself is spinning and therefore it has angular momentum. This will be a vector pointing downwards along the axis of the top. Once again, this is found from the right-hand grip rule. Imagine gripping the axis of spin with the right hand so that the fingers go around in the direction of rotation. Then the angular momentum vector is shown by the thumb direction. We would call this the spin angular momentum S, and we could write the size of it as I omega. That's analogous to mass times velocity for momentum in linear mechanics. So, as far as rotational mechanics is concerned, there are two vectors involved here. A torque pointing out of the screen and an angular momentum along the axis of the spinning top. Now just as in linear mechanics a linear force changes linear momentum, so in rotational mechanics a torque, which is a turning force, changes angular momentum. That means this angular momentum vector S of the top cannot stay as it is. The torque, turning force out of the screen, will change it. And if you do the maths working with these two rotational vectors, torque and angular momentum, you see that the torque doesn't actually change the size of the angular momentum. It doesn't spin faster or slower, but it does change the direction. That's the effect the torque has on the spinning top. This is because the torque vector is acting at 90 degrees to the angular momentum vector. If it was in the same direction as the angular momentum, it would make the top spin more quickly or more slowly. But as it is at right angles to it, it can't affect the rotational speed. If you want an analogy, it's a bit like circular motion in linear mechanics. If that doesn't sound too stupid, circular motion in linear mechanics, but it's true. In that situation, if you've studied it, you will know that the force to the centre of the circle changes the velocity and hence the linear momentum of the object, but it doesn't change the size of the momentum or the velocity. It doesn't make it move any faster or slower, it changes instead its direction. And if the force keeps on acting perpendicular to the direction of travel, in other words radially, it will keep on changing its direction, and the object will travel in a circle at a constant speed, but with a changing velocity. Remember, velocity is a vector, whereas speed is a scalar, and is the magnitude or size of the velocity. Here, with this rotational situation, and the top leaning to the left, the effect of the anti-clockwise torque out of the screen is to make the angular momentum arrow change its direction. It makes it point in a different direction, and so the precession begins. In fact, the direction of the angular momentum keeps on changing because the torque keeps on acting at right angles to it, and the top precesses around the vertical, around the direction of gravity. Just as with circular motion, where the force itself keeps changing direction as it points towards the centre of the circle, so here the torque keeps changing direction as the top precesses. Here it's clockwise and into the screen, and here it's anti-clockwise and out of the screen. So the analogy between circular motion in linear mechanics and precessional motion in rotational mechanics is pretty close. In circular motion, we have a force of constant size acting at right angles to linear momentum of the object, and it keeps at right angles to it. The moving object travels in a circle around a point to which the force is directed, and the size of the velocity and momentum stay constant, although their direction changes. And in rotational mechanics, a torque of constant size acts at right angles to the angular momentum of the spinning object and keeps at right angles to it. The spinning object precesses around the direction of the forces making up the torque, and the size of the angular velocity and the angular momentum stay constant, although their direction changes. I must say, however, that even though I understand the mathematics of this motion, and I accept it, and it makes sense, there's still something in me that finds this gyroscopic spinning top motion counterintuitive. As I watch a spinning object not falling over and precessing, there's still a feeling that it ought really to fall down. And maybe there's an analogy here as to how most people who've studied quantum mechanics feel about it. We'll do some of this later, but you can easily get to the point where you accept the mathematics of quantum mechanics and even understand that side of things, but there's still a niggling feeling that something else ought to happen from what the mathematics predicts and from what actually happens. The mathematics agrees with reality, but somehow it never quite seems to make sense. I will only touch on some of the mathematics of quantum mechanics in order to think about entanglement, and even the little bit we do won't be easy, but even those who've studied mathematics much further will probably admit that they may well understand the mathematics of it and accept its conclusions and use its rules to explain and predict phenomena, but it never really makes sense to our classical way of thinking. Just as you may understand the mathematics of the spinning top and accept its conclusions and realize that it predicts reality, but still have the feeling that the top should fall over, so when we do a bit of quantum mechanics, you may well accept the mathematics of it and understand the rules, but it won't really make sense. However, in order to understand the mathematical rules better, I said that I believe it's good to have a reasonable understanding of what we're going to mean by the words spin, angular momentum, and magnetic moment, because these terms are going to crop up again and again. So how does this spinning top idea and the idea of precession relate to what will eventually be our main focus, spin? Well, in order to get to that, you may remember that we were thinking about magnets, and I'd introduced the fanciful notion of a magnet in a magnetic field and at an angle to it being held there somehow, ignoring gravity. I then suggested that if the magnet was somehow spinning and could be held there, then when it was released, again ignoring gravity, it would precess around the magnetic field. The argument is that the magnet, being made of metal, clearly has mass, and that mass is not at a single point, but is spread out over its shape around the axis down the middle. In physics parlance, that means that the magnet has moment of inertia. And in particular, it has a moment of inertia about the axis of rotation. Then, because it is spinning, as illustrated by the little circle around its waist, we can say that the magnet has spin angular momentum, I omega. So once again, there are two vectors which are directly associated with this particular magnet, both of which are along the axis. There's the angular momentum vector I omega due to its spinning, shown here with a blue arrow, and there's the magnetic moment vector mu, which we discussed earlier, which is now shown by the red arrow. I'm sure you realize that these are two very different things. The magnetic moment is because of its magnetic properties and always points from south to north. The angular momentum, on the other hand, is because of its mechanical spinning motion, and its direction depends on how the magnet is spinning. In this case, it is spinning anti-clockwise from below, so the angular momentum vector points downwards. This is found once again using the right-hand grip rule. Imagine gripping the magnet with the right hand so that the fingers point in the direction of the spinning motion, and then the thumb will point in the direction of the angular momentum vector I omega, in this case downwards. So again, if you are now somehow restraining this spinning magnet to stay in this position, and you then let go, then there are, going from first principles, there are 3 vectors altogether to think about. 2 for the magnet and 1 for the field. The magnetic field B is upwards. The magnetic moment mu goes from south to north within the magnet, and the angular momentum vector I omega is downwards again within the magnet. However, we discussed before how that 2 of these vectors, the magnetic moment mu and the magnetic field B, produce a turning force or torque given by tau equals mu cross B, or tau equals mu B sine theta. In other words, the magnetic moment mu and the magnetic field B produce a torque which is into the screen in this case. We got this from the right-hand rule applied to mu cross B earlier. So instead of the 2 vectors magnetic field B and the magnetic moment mu, we can think just in terms of the torque that they produce, tau. In all, therefore, as far as the mechanics is concerned, there are 2 vectors to think about, vectors relating to the bar magnet and its motion. The torque tau into the screen and the angular momentum I omega downwards within the magnet. The torque into the screen should probably be shown by a circle with a cross into it, in it, indicating that it is into the screen, but I will leave it for now as a rotational arrow. The point is that these 2 vectors, torque and angular momentum, are at right angles to each other. This means that, just as in the case of the spinning top, the torque, instead of forcing this magnet to go to the upright position, makes it execute a precessional motion around the lines of the magnetic field. If the bar magnet itself wasn't spinning and had no angular momentum, then it would simply oscillate backwards and forwards. Now, I've gone through all of this detail about magnetic moments and precession because it will be relevant when we come to think about electrons and quantum mechanics. At that point, we will look at how quantum mechanics can explain the phenomenon of the precession of electrons in a magnetic field. Before we get anywhere near there, however, it's probably worth briefly looking at the idea of electron precession from a classical point of view. I'll state it simply for the moment and then look at the detail. Here's an electron imagined as a sphere in a magnetic field. As I mentioned before, electrons have a magnetic moment in the same way that a magnet does, and I'll show it as a red arrow through the electron. In this case, I'll assume the magnetic moment is at an angle to the magnetic field, like this. Also, even though they are ridiculously small and light, electrons have some sort of spin angular momentum, S. Again, we'll discuss this more later, but they are essentially like a spinning magnet, although very different. I'll represent this by a black circular arrow showing an anti-clockwise spin as seen from below. I could equally well show this as an angular momentum vector pointing downwards. Remember the right-hand grip rule again. Having a magnetic moment, which is the red arrow rather than the blue, means that even thinking classically and very simplistically, there is going to be a clockwise torque on this electron as we look at it. That's from the fact that the magnetic moment is in a magnetic field. So it will begin to align itself to the field. However, again thinking classically, the electron has a spin angular momentum, like the spinning magnet. So in trying to turn to align itself with the direction of the magnetic field upwards, the electron will undergo precession. That's probably enough for now on that, although I will return to this classical precession of the electron before moving on to do some quantum mechanics. It will be useful to delve into classical electron precession in a bit more detail and to be more comfortable with it before we use quantum mechanics to explain what's really going on. However, Before we move on to any of that, I'd like for completeness to look at a different type of magnet and consider the idea of its magnetic moment. The magnet I want to look at is what is often called a current-carrying solenoid or coil. The one shown here is a long coil which has a current I going in on the right and coming out on the left. If we were to look at the coil from the right hand side, the current would be going in clockwise circles around the coil. You should already know that a solenoid or coil of wire which has a current passing through it resembles a bar magnet in many ways. You've probably seen patterns of the field lines around each of them, and they look very similar. The current-carrying solenoid has a north end and a south end, just like a bar magnet, and which end is which can be found using the right-hand grip rule. The current through the coil in this case is going around clockwise if you look at it from the right hand side, and the right hand grip rule says that if you place your right hand so that your fingers follow the current direction, then your thumb will point towards the north end of the solenoid, in this case the end on the left. It should be fairly obvious then that if a solenoid has a current passing through it, and if it then looks exactly like a bar magnet, then it will have a magnetic moment, mu. And just as in the case of the bar magnet, that magnetic moment will point from south to north inside the coil. This means that if you were to place a current-carrying coil into a magnetic field at some angle, there will be a turning force, a torque on it, providing the coil has a current passing through it, of course. This picture shows such a coil in a magnetic field B and at an angle to it, just like we had with a magnet. Never mind how the current gets into or out of the coil, or how the coil is suspended in mid-air. Once again, it's an imaginary situation. The north end of the coil will experience a force F in the direction of the magnetic field, which is upwards, and its south end will be pulled with the same size force in the opposite direction. These two forces will produce a couple or torque on the coil, which in this case will be clockwise as we look at it. The torque will be a maximum when the coil is at right angles to the field at 90 or 270 degrees, simply because the separation of the two forces is greatest, and it will of course be zero when the coil is parallel or anti-parallel to the field. The torque will obviously have some other value at other angles, theta to the field. We haven't thought yet as to what exactly we could write down for the magnetic moment of the coil, but clearly it will once again relate the torque it experiences in the field to the value of the field in which it's situated, in exactly the same way as we had before. Don't forget, that was how magnetic moment was defined. It's the constant between torque and field, so that we must have tau equals mu b sine theta. Also remember that this vector formula for tau equals mu cross b, includes the value of sine theta from the idea of the cross product. Size-wise, these two are the same formula. So what exactly is the expression for this mu, the magnetic moment of a current-carrying coil? Can we calculate it? Or like the bar magnet, do we have to find it out by experiment and through using this formula? Well, I think it should be obvious that the magnetic moment mu of the coil, which is to do with the strength and dimensions of the magnet that it makes, will depend on the dimensions of the coil and on the current passing through it, so it should be calculable. Strangely, or at least strangely at first sight, the magnetic moment of a coil does not depend on the length of the coil. I say strangely because with a simple bar magnet it seemed obvious that you get a bigger magnetic moment and hence a bigger torque for a longer magnet, assuming you've got the same pole strength. Whereas here it turns out that with a current-carrying coil, the magnetic moment mu only depends on the following three things: the area of the coil, the number of turns of the coil, and the current passing through the coil. So, if I illustrate the magnetic moment vector as a red arrow inside the coil, which is going from south to north, then this long coil gives exactly the same torque as this squashed coil in a uniform field, providing they have the same area, the same number of turns, and the same current in them. The long and short current-carrying coil each has exactly the same magnetic moment mu. In fact, it's very easy to show that the torque on a current carrying coil in a uniform magnetic field B is given by tau equals NIAB sine theta, where N is the number of turns of the coil, I is the current in the coil, A is the area of the coil, B is the magnetic field, and theta is the angle between the coil and the field. There's no length of the coil involved in this formula. Some of you may even have proved this formula at school level when doing the theory of a moving coil meter, those meter movements used in old-fashioned ammeters and voltmeters. For the proof of that formula, you consider a single turn square coil in a uniform magnetic field B, where the angle theta is between the field and the perpendicular to the plane of the area. Essentially, you work out the up and down forces in these two bits of the wire, knowing the formula for the force on a current carrying conductor. Then, along with the other length, these forces give the couple or torque, and the value of it, for n turns, not just one, works out to be tau equals NIAB sine theta. It's a very straightforward calculation. Some of you may remember that when discussing the moving coil meter in school, you get rid of the sine theta by curving the pole faces to give what is sometimes called a radial field, in which case tau equals NIAB. Looking from above, you can see that you then put the coil close to and around a soft iron core, restrain it using some springs, add a pointer and a scale, and you then have a meter which gives a deflection which is proportional to the current. If you haven't done this before, it doesn't matter. Just realise that in a uniform magnetic field, not with curved pole faces, a coil of area A and n turns, long or short, with a current I passing through it, will have a torque on it of tau equals NIAB sine theta, where theta is the angle between the field and the coil. Clearly, you'll get more turning force or torque if the current is increased. That should seem sensible. You're making the coil into a stronger magnet in the field. You'll get more torque if the number of turns is increased. Again, that should seem reasonable, as each extra turn in a way gives more current going around the coil, and you'll get more turning force or torque if the area of the coil is increased. Now that's perhaps not so immediately obvious without going into the proof of how the torque came about or going into the idea of magnetic flux lines and the like. But I hope the formula seems at least reasonable. As I say, it's certainly easy to prove if you want to look into it. The main thing is, however, that the torque on any shape of current carrying coil placed in a uniform magnetic field and at some angle theta to it is given by the formula tau equals NIAB sine theta. Doesn't have to be a rectangular coil, doesn't have to be a circular coil. Any shaped coil will produce this torque, and it can be long or short. So if we compare this with our simple formula which relates torque with magnetic moment, it's fairly clear that magnetic moment mu of a current carrying coil must be NIA. In other words, the magnetic moment of a coil of n turns with current in it and having cross-sectional area A is given by mu equals NIA. This magnetic moment depends only on the number of turns of the coil, the current passing through it, and the area, and is equal to the three of them multiplied together. In a way, of course, the number of turns times the current is the total current going round in the loop of the coil, so that the magnetic moment only really depends on the total current going around and the area. You can probably see more clearly now that the units for magnetic moment mu, which were more obviously Newton meters per Tesla or joules per Tesla from mechanical considerations, can actually be written as amps meter squared, which is current times area, the number of turns being irrelevant as far as units are concerned. You should by now realise that when such a coil is in a field and has a current through it, then just as in the magnet situation, you would need to do work to rotate the coil from its equilibrium position to some position where its magnetic moment was at some angle to the magnetic field. This means that when the coil is in this position, it would have increased its potential energy from zero. We said before that if you take the equilibrium state as having zero potential energy, in other words when the magnetic moment is in the direction of the magnetic field, then the energy of the three main positions at 0, 90 degrees and 180 degrees are 0 for 0 degrees, the upright position, by us defining this as 0, mu b for the 90 degree position, or 270 degrees as well, and 2 mu b for the 180, the upside down position. For the coil with current in, of course, we can now replace mu with NIA, so that we then have, again, 0 for the 0 degrees upright position, NIAB for the 90 degree position, and 2 NIAB for the 180 degree or upside down position. Clearly, in this case, however, there's not really any sense in which the coil could possibly have angular momentum. It's not like a spinning top. The only thing going round and round in this coil are the electrons which make up the current I. The mass of the electrons of that current is negligible, so that the angular momentum is effectively 0. This means that if, in this imaginary situation, the coil is released from some position where it has potential energy but keeps its current, it should go straight back to the equilibrium position, overshoot and oscillate backwards and forwards until somehow the energy gets dissipated. There will be no precession around the magnetic field lines. All of what has been said for this multiple turn coil would obviously also be the case for a single turn coil with current in it. If you can imagine a single turn coil or ring which somehow has current in it, we won't ask how the current gets in and out, which is then placed in a uniform magnetic field, it would simply oscillate from side to side with no precession. We could think of it as its magnetic moment oscillating, which is actually the case of course, but what would be seen is a simple coil oscillating. I should mention again that this contrasts with the situation we will have later for an electron in a magnetic field. As has been said, the electron not only has magnetic moment, but it also has angular momentum as well, so that even thinking classically about what might happen, an electron will precess around the magnetic field lines when it is released, if I can use that word released when talking about an electron. Even later on still, when we're into quantum mechanics, we'll see that although the mathematics of quantum mechanics treats things very differently, we can still talk about something similar to classical spin precession when discussing electrons in a magnetic field. Okay, moving on. Before we can begin to think about what's the big deal over entanglement and get into some of that quantum mechanics, I'd like to look at the energy states of an electron in a magnetic field. We've already looked at the energy of the three positions for a bar magnet and for a current carrying coil. This is what we found for the bar magnet. When upright with its magnetic moment in the direction of the field, the bar magnet energy was defined to be 0. Then at 90 it was mu b, and at 180 degrees it was 2 mu b. For the current carrying coil, the magnetic moment was calculable in terms of the coil and the current in it, so the energies were simply 0, NIAB and 2 NIAB. Now, I want to do the same for an electron. I'd like to be able to write down the energies for an electron with its magnetic moment at 90 degrees and 180 degrees to the field. And that's where the next video will start.